Let's look at section 11.4, functions and their graphs. Recall the function f of x equals the absolute value of x has a V shape. We know the absolute value function has a V shape. Let's review what it looks like. We'll look at x and f of x. I'm going to pick -2, -1, 0, 1, and 2. These are random points, but they will give us the general shape of the absolute value function. The absolute value of -2 is a +2. Absolute value of -1 is a +1. And so on. We have the absolute value of 0 is 0. The absolute value of 1 is 1. And the absolute value of 2 is 2. If we plot the points, we have -2, 2, -1, 1, 0, 0, 1, 1, and 2, 2. This is our function. It has that nice V shape, and just like the parabola, this is the parent graph. This is the parent graph of the absolute value function. And so if we remember this shape, we can graph pretty much every single absolute value function. It goes left 1, up 1, and then from the vertex we go left 2, up 2, right 1, up 1, and right 2, up 2. So it's very important that we remember the shape of the parent graph. Let's go over the shape one more time. We start at the vertex, we go left 1, up 1, and then we restart at the vertex, left 2, up 2, right 1, up 1, then right 2, up 2. Let's graph another function. Before we graph another function, if a is greater than 0 or positive, we have a v that's facing up. If we have a is less than 0 or negative, you're going to have a v facing down. HK again represents our vertex. It's very similar to the parabola. HK represents our vertex, the turning point of the graph. Before we sketch a graph, you always have to find the vertex, h, k. The h is a +3 and a k of +4. Let's graph the vertex 3, 4. And now this is a absolute value facing up, so we know it's a v facing up. We have left 1, up 1 as our second point, left 2, up 2, and you always restart at the vertex, right 1, up 1, right 2, up 2. So this is it. This is our absolute value. All that happened was it got shifted to the right 3 and up 4. We have to state our domain. The graph goes forever to the left. It goes forever to the right. So the domain is -infinity to infinity. For the range, it goes down to 4. But it goes up forever. So the range is square bracket -4, or actually +4, and it goes up forever. Let's try another graph. This has a leading coefficient that is also positive, so it's going to look like this, a V facing up. The H, we have to be careful. This is where a lot of students make the mistake and tell me H is +1. That's not true. If you were to rewrite this, it's x minus a -1 plus 5. So the absolute value of x minus a -1 plus 5. This is the h, this is the k. So our vertex is actually -1, 5. So be careful. You have to consider the plus inside the absolute value as a double negative. it gets shifted to the left 1 and up 5. And then we'll draw our parent graph at this location. Left 1, up 1. Left 2, up 2. Right 1, up 1. And right 2, up 2. The shape of our parent. For the domain, it goes forever to the left. It goes forever to the right. So it's from negative infinity to infinity. For the range, it goes down to here. That's the highest, or actually the lowest value for the y. So that's the range. Goes down to 5, but it goes up forever. The range is square bracket 5, comma, infinity. In this graph, we have a negative 4. So our vertex is going to be easy to find. This is going to be 4, comma, negative 2. This is my h. This negative 2 is my k. That's the vertex, 4, comma, negative 2. It has a positive leading coefficient. So we're just going to have a regular V-shaped absolute value function. Again, it's left 1, up 1 from the vertex. Left 2, up 2 from the vertex. Right 1, up 1 from the vertex. And right 2, up 2. So here is our domain. It's the same as before. It's negative infinity to infinity. For the range, I always look at the picture. How far does the graph go down? It goes down to here. That's negative 2. How far does it go up? Well, it goes up forever. So it goes up to infinity. This sketch is different. We have a negative. What does that mean? It's going to be a V facing down. So just remember, you're going to flip this graph upside down. What's our vertex? H, comma, K. This is the H, which is a positive 2. And the K is a negative 3. So this is our vertex, 2, comma, negative 3. Let's graph that right here. So we go left 1, but we don't go up 1, we go down 1. Left 2, down 2, because it's flipped upside down. Right 1, down 1. Right 2, down 2. So all of the function values are flipped. So if you look at our original table for the parent graph, it was like this. Negative 2, negative 1, 0, 1, 2. And we said this was 2, 1, 0, 1, 2. So at the top of the page, or at the top of this worksheet, we would have this as our absolute value of x. But what happened when there's a negative? All of these became opposite. So instead of going up 2, we went down 2. We went down 1. Stayed the same. The vertex didn't move position. But we did the opposite. So it's an upside down V. And we can now read the domain and the range. The domain is still the same, but the range is different. It goes down forever. So the negative infinity is actually first, and it goes up to the highest value, which is negative 3. That's a square bracket for that, negative 3. We have another parent graph. This is the square root function. The square root function. For the square root function, we'll make another table. And we're looking for the square root of x. But I cannot pick negative values because negative values will give us an imaginary result. So we'll pick some easy square roots. 0 is a very easy one to pick. The square root of 0 is just 0. The square root of 1 is just 1. I don't want to pick the square root of 2 because I don't know what that is. It's a decimal. It's very hard to graph. Square root of 3 is also difficult. We can use the square root of 4, which gives me a 2. And square root of 5 is difficult to do, square root of 6 is difficult, but the next easy one is the square root of 9, which gives me 3. So I can graph these points to form my square root function. Again, this is a square root function, which would be another parent graph. 0, 0, 1, 1. So we go 0, 0, right 1 up 1. Right 4, this time, this one says right 4 up 2. And unfortunately, we cannot fit 9, 3, but if I had space, I would put it in the graph. So the square root function looks something like this. It starts at an endpoint, so this is our endpoint. It's not a vertex because it doesn't change direction. So this is our endpoint or our starting point. And it goes to the right 1 up 1, and then we go to the right 4 up 2. So it does look like a parabola turned sideways, but it's missing half of its side. So this is just half a parabola turned sideways. The square root function still has this nice form. The x minus h is inside the square root plus k, where the endpoint is located h comma k again. Just like our vertex, the endpoint is hk. Try to graph some square root functions now. Always start with your hk. Where is that endpoint? We have h is a positive 2 and k is a positive 6. So we'll start with the endpoint. 2, 6. And if you remember the shape of the original parent graph, it's right 1 up 1, right 4 up 2. So we'll draw that here. Right 1 up 1, right 4, 1, 2, 3, 4 up 2. And so I have that nice smooth curve now. It's half a parabola. What is our domain? Well, the domain is how far left it goes to how far right on the x-axis. So it goes to the left, -2, and it goes to the right forever. For the range, you're on an elevator on the y-axis. It goes down, the lowest point the y can go to is the 6. So this is square bracket 6. Goes up forever, so we'll say it goes up to infinity. Let's look at this graph. This is x plus 1 inside the square root minus 2. I can rewrite this as the square root of x minus a -1 minus 2. This -1 represents my h, and this -2 represents my k. So the endpoint h comma k is -1 comma -2. Again, a lot of people confuse the h with being a positive 1, the most common mistake. And so we're going to go to the right 1, up 1, to the right 4, 1, 2, 3, 4, up 2, and we'll get a nice, smooth square root function. We can now state our domain. Our domain is how far on the graph does this graph go on the x-axis. Well, it goes only to -1, so it goes left -1. How far to the right does it go? It goes to the right forever. So the domain is -1 to infinity. For the range, it goes down on the y-axis only up to -3. So the lowest point is -3. Goes down all the way here to -3. Nope, that's a mistake. Let's fix that. It's actually -2. Let's write that as a -2. The lowest point is -2. And it goes up forever, so we'll say infinity. So again, the domain is how far left it goes to how far right it goes. The range is how far down it goes to how far up it goes. In the next graph, there's a negative. That means instead of our graph looking like this for the square root, that's not what we want to do. We want to make it upside down. So flip it upside down. So we'll flip it like this as it goes to the right. It's still a parabola facing right, only half of it, but it's the lower part, not the upper part. I can rewrite this with a double negative so I don't get confused. This is my H, this is my K. My endpoint is the point HK, so we'll write H as -1 and K as -5. And so we have to be careful with this one, it's going to be upside down. So typically we go right one and we would go up one, but it's opposite now. So we're going to go down one. We go right 4 spaces. And normally I would go up 2, but since it's upside down, I'm going to go down 2. And so it looks like a parabola, just half of it. And it's facing to the right. So we'll state our domain and range now. The domain is it goes to the left. It goes to the left just to -1. That's the farthest left it could go to -1. I should use a square bracket. It goes to the right forever, so we'll use an infinity. For the down part, it goes down forever. This thing slowly goes down. That's -infinity. But it only goes up to here. The highest point is -5 for the range. And we'll use a square bracket. This one's going to be different because the negative is on the inside. So for this, I like to make another table. And we'll plug in some values. If I plug in a 0, this is the square root of -0, which is pretty easy to do. That's a 0. If we plug in a 1, it would not work because we'll be taking the square root of -1. And that is not going to work. We don't know how to graph I on the Cartesian plane. But if I use a -1, look at what happens. We plug it into the original equation. We get a square root of a +1, which we all know is just 1. So we can use -1, and we could use -4 instead, and that's going to give us some nice values to graph. So let's plot the square root of a negative on the graph. So we have 0, 0, that's our endpoint. But this time we go left 1, up 1, and left 4, up 2. So what happened? If the negative is on the outside, it flips our graph upside down. If the negative is on the inside, it flips it to the left. So that's something to be aware of. If the negative is inside the radical, it switches the graph to the left. If it's on the outside, it flips it upside down. So that's something to remember. If the negative is on the inside, if it's on the inside of that radical, we're going to flip it to the left. That's something to remember. So we'll start with this graph. F of x equals the square root of negative. Look, the negative is on the inside. So that means we're going to have to flip it to the left. That is something to remember. And I can rewrite it again so it's a double negative. So this is my h, and this is my k. So the endpoint, let's write the endpoint, h comma k, is -4 comma -2. So that is the endpoint. But remember, this faces to the left. So we're going left 1 up 1 and left 4 up 2. So the endpoint is easy to find, but this time it's facing to the left. Because of that negative right here inside the radical, forcing our graph to face left. What if it's negative on the inside and negative on the outside? Well, it's going to be facing to the left, and it's also going to be upside down. Let's graph a cubic function and see what this thing looks like. Again, we're going to make a table. We'll have x and f of x. I like to plug in -2, -1, 0, 1, and 2. Again, you can pick different points, but these are good points to pick. -2 cubed is -8. -2 cubed is -8 because you're multiplying -2 times -2 times -2. -1 cubed is a -1. This is 0. 1 cubed is 1, and 2 cubed is 8. Let's graph this thing out. Let's see what it looks like. We'll start with -2 comma -8. -1 comma -1. 0, 0. 1, 1. And 2 comma 8. So this is a cubic function. It looks kind of like an S. So it has a smooth curve, and it pretty much forms an S shape. The domain for this is -infinity to infinity because it goes to the left forever, to the right forever. And the range is also the same because it goes down forever and up forever. The domain and range for the cubic function is always the same. It's -infinity to infinity for both cases. Again, you have to be careful. There's an h and there's a k here. The h and k does not represent the vertex. Our hk here is 1 comma 1. It does not represent the vertex because cubic functions don't have a vertex. This is where it starts changing direction. We actually call it an inflection point. This is not a vertex or an endpoint. It's called an inflection point. So HK here represents our inflection point. And just like before, we have that standard form. Where this HK represents our inflection point, and the leading coefficient tells us if it's facing up or down. If it's negative, it's going to be flipped upside down. If it's positive, it's the original parent graph. So let's graph -1 or 1 comma 1 for our inflection point. 1 comma 1. Again, don't make the mistake. This is a -1, so our h is a +1 and our k is a +1. For this graph, you want to go left 2 and down 8. 1, 2, 3, 4, 5, 6, 7, 8. From the inflection point again, left 1, down 1. So we have part of the graph. And then to the right 1, up 1. And to the right 2, up 8. 1, 2, 3, 4, 5, 6, 7, 8. So we have a smooth curve. It's pretty difficult to draw, but try your best. You will not be graded on your art skills. Just make sure you connect all the points in a nice smooth curve. And the domain is it goes to the left forever, to the right forever. The range is the same because it goes down forever and it goes up forever. The range is the same. This is going to be a similar process. Let's look at our function. Let's rewrite it as a double negative so we don't get confused with hk for the inflection point. We do have a k. The k is an invisible 0. So the h is a negative 3 and our k is a positive 0. That's the inflection point. H comma k is going to be negative 3 comma 0. This is going to tell me the graph is upside down. So instead of an S like this, that's not what we want. We want an S like this. So it looks like a mirror reflection. It's reflected about the x-axis. So let's graph negative 3 comma 0. That's our inflection point. So when we go left 1, typically we would go down 1, but I'm going to go to the opposite direction because it's upside down. So we'll go up 1. Left 2, I would go typically down 8, but we're going to go up 8 because it's upside down. Again, you always start at your inflection point HK. To the right 1, I would normally go up 1, but we're going to go upside down, go down 1. To the right 2, again we go down 8, the opposite of the regular cubic function. So we're going to draw a sketch here, being careful to make it a smooth curve. And you could always check your work by going to Desmos.com and graphing these functions. It's really easy to graph these on Desmos.com so you can see what your graph looks like. Again, Desmos.com is a free graphing tool for you to graph these functions. In the next question, we are asked to determine what is the original function. This is a square root function, so all we need to do is tell the person what hk is. So let's look at the graph. The endpoint here is located at -9, comma, -4. This is my h. This is my k. So if I were to rewrite this as the original function, it would be x plus 9. The reason it's plus 9 is because h is -9, and k is going to give me a -4. So the -4 is outside that radical. This is my original square root function. Let's find the original function. This is a cubic function. So we'll need to find hk. H here is a -6. K here is a 4. So if I rewrite my original cubic function, since this is a negative h, remember, this is always opposite of what you think for the h, so this is a +6 on the inside. Cube it, because it's a cubic function, and k is what we see is what we get, so it's a +4. This is our original function. It's a cubic function. I know it's the regular one. It doesn't have a negative in front because it's an S shape with the tail on the left going down and the tail on the right going up. Determine the original function. In part A, this is a square root function. So let's write the general form for that square root function. And so all we need to do is fill in the blanks. What is h? H, well, we'll need to look for the vertex first. This is 2, 5. This is my h. This is my k. So the vertex is 2, 5. So what is my original function? Based on the graph, it should be the square root of x minus 2. That's h is a +2. And k is a +5. So this is our original function. For the last graph, this is an absolute value graph, so recall the standard form for the absolute value graph. let's figure this out. What is the vertex? The vertex is -4, comma, -2. That means my h is -4 and my k is -2. So when we rewrite this, it should be x plus 4 on the inside. It's a plus because it's opposite for the h. And the k is going to be -2. This is the original function. It's an absolute value function that gets shifted left 4 and down 2 units.